Lambda is called an eigenvalue of a matrix A if there exists a non-zero vector V, called an eigenvector, such that A times V equals lambda times V. In other words, the matrix stretches or shrinks this special direction, but never rotates it. To find the eigenvalues, we solve the characteristic equation, the determinant of a minus lambda times the identity matrix equals 0. Let's work a full example. Let A equal the 2 by 2 matrix with rows 3, 1 and 0, 2. We compute A minus lambda times the identity and take its determinant. This gives us the characteristic equation, open bracket, 3 minus lambda, close bracket, times, open bracket, 2 minus lambda, close bracket, equals 0. This factors immediately, so the two eigenvalues are simply lambda equals 3 and lambda equals 2. Now we find the eigenvector for each eigenvalue, starting with lambda equals 3. We substitute into A minus lambda times the identity, giving the matrix with rows 0, 1 and 0, minus 1. Row reducing this matrix tells us that x sub 2 equals 0, while x sub 1 is free to be anything. Choosing x sub 1 equals 1, our eigenvector for lambda equals 3 is the vector 1, 0. Next, we repeat the process for lambda equals 2. Substituting gives A minus 2 times the identity, equal to the matrix with rows 1, 1 and 0, 0. Row reducing here tells us that x sub 1 equals negative x sub 2. Choosing x sub 2 equals 1, our eigenvector for lambda equals 2 is the vector negative 1, 1. So notice the two-stage process. First, we solved one characteristic equation to get both eigenvalues, 3 and 2. Then, for each eigenvalue separately, we solved a fresh system to get its own eigenvector, giving us the vector 1, 0 and the vector negative 1, 1. Like and follow for more math tutorials, one idea at a time, nothing rushed.